So hopefully in the last video you noticed that the individual voltage drops actually added up to the total voltage. And this was no accident. In fact, this is a mathematical law, and it's known as Kirchhoff's voltage law. So who Kirchhoff was, and let's actually pick a different color here. Who Kirchhoff was a scientist who kind of figured out these principles that we've been discovering the last few videos. And what his voltage law states is that individual voltage drops actually add up or equal, let's say, equal the total voltage. And if you think about it, this makes sense. And we kind of discovered this idea in the last few videos, like I said. So why does he get it named after it if we can figure it out? Well, because he was the first one to figure it out, so he's special. But using a variation of this law, there are a couple of implications, and these are also implications that we have also discovered. And the first one is, let me pick my right color here so we can keep everything consistent, is that current is constant. Let's not say constant or consistent. Constant in a circuit with resistors in series. We figured that out already, which is kind of awesome that we can figure it out together as a class, this sort of mathematical principle. But the next implication, using another variation of this formula, we can say something else that we've already figured out, and that is that individual resistors, and let's capitalize correctly here, keep it somewhat grammatically correct, but individual resistors add up to the total resistance. And so again, using these ideas that we've discovered, Kirchhoff actually figured out on his own. And he figured it out using this very simple formula, which is the voltage law, and that is the voltage total equals the individual voltage drops. And if there's more than 3 voltage drops, then it would continue on for however many voltage drops there are. And in actuality, what it says is that the voltage total plus the voltage 1 plus voltage 2 plus voltage 3 equals 0. Because the voltage is dropping, it is 20 volts, and then it's dropping a certain amount, dropping 4 volts, then 6 volts, and then 10 volts, all the way down to 0. But I find this variation of the formula a little bit easier to work with. And you might be wondering yourself, what do you mean, Mr. Anderson, when you say using variations of the formula? So let's go ahead and rewrite this formula using the very simple idea that V equals IR. And no, that's not a smiley face. That is a drop-down arrow saying, let's rewrite this formula. But we can rewrite V total as I times R, or in other words, current times resistance total. Because it does equal that. And then voltage 1 can be represented as current times resistance 1, because it does. We said these are equal, which makes them interchangeable. Then we can rewrite it again. Current times resistor 2 is the same thing as saying voltage 2, and then we can add current times resistor 3, which is the same as saying voltage 3. They are interchangeable, as we've discovered. And so this is the part of the formula that implies that current is constant here. As you can see, the current isn't changing, whereas the resistors are. And in fact, we can go one step further. We can rewrite this again to say current times resistance total equals current, and then we can just sort of FOIL it out, times resistor 1 plus resistor 2 plus resistor 3. And since it's multiplying by all of them, we can just leave it here outside of the parentheses because that kind of means the same thing. But if we write it this way, what we can actually do is really quickly and really easily divide by current. And we get something really cool happen here if we divide by current on both sides. And that is, when we rewrite this equation again, we get that formula that resistance total equals resistance 1 plus resistance 2 plus resistance 3, or in other words, individual resistors add up to total resistance. And so what we just did is a mathematical proof of Kirchhoff's voltage law and its implications.